Hello, everyone. Thank you, Ava, for coming and attending my presentation. So today I'm going to talk about the modeling of environmentally responsible supply chains. I am Ehab Bazan, a PhD candidate at the Department of Mechanical and Industrial Engineering, and I'm working under the supervision of Dr. Jabber. Just briefly, I'm going to go through my presentation, just present what the motivation for my research area is, a brief introduction, the problem, the current scope, my current work, and future work, and then I'll be open to take your questions. So there's a lot of talk about saving the environment, and if you Google online, you'll find there's many things. Yeah, your foot, you step on the cable. There we go. So there's lots of stuff on the internet where everyone wants to save the environment. You can find like 100 steps. Here's what to do. Use more emails, less paper. Recycle. Turn the lights off when you're not using. Make sure the faucets are safe. That's nice. It's interesting. But what I want to do is take those same steps that we do in our day-to-day lives and apply it to my research topics, which is inventory and supply chain management and what we like to call environmentally responsible supply chain. So the approach, me being a mechanical engineer and an industrial engineer, you always want to apply, do something, and you want to see what you've built actually work. So you build a car, you see it run. So if you design a model, you want to see it operate. So, and as a change agent, you want to change the philosophy on how people are modeling supply chain and inventory systems, not just being focusing on costs. So I'm trying to do something on the operational level as sort of a decision support system, maybe. So supply chain management in general, what this is there's a variance between supply of a certain product and the demand. And from here, we need to have some management of these discrepancies. And an effective supply chain is one that's essential for any business. Then people are now talking about this environmental awareness in supply chain. So it's taking that environmental thinking, those 100 steps of how to protect your environment, and applying it into the supply chain management, right? And it's, if you are talking about your sustainability of your business and sustainability of your environment and the well-being, this is needed. A basic definition for supply chain management, there's numerous ones. I like this one because it focuses on three things that I like to present. It's the systematic strategic coordination of traditional businesses. And it's also, it's just the definition for supply chain management. Green supply chain management is the integration of the environmental thinking into supply chain management. So in the industry, Canada, the Supply Chain Logistics Association Canada, they say that it includes the introducing technical and innovative processes into material sourcing and selection, delivery of the final product, and end of life of management. Basically, the wished for result is the improvement of organizations of their environmental impact while increasing their efficiency. So you're not losing any of the financial benefits, but you're also gaining the environmental thing. So sort of the evolution of the terminologies, people started focusing on, okay, from inventory models, reverse logistics. That is, forward products are going to the customer, recollecting them back from the customer, back to the manufacturer. Closed loop supply chains is when we put both the forward together and backward, and the reverse logistics, green supply chains, people started to implement these environmental thinking and then sustainable supply chains total. So that's sort of like the evolution. Some practices and benefits of green supply chain management include being energy efficient, reducing waste, water conservation, green procurement practices, recycling of product and packaging, and so forth. When I was surveying the literature, what we found out is the majority of the literature is qualitative in nature. Basically, someone is saying, okay, let's protect the environment. It's nice to protect the environment. And he says, okay, so this is what I suggest we do to protect the environment. Here's a couple of frameworks. Here's a couple of, okay, this is nice. What is it that I'm actually going to do? Right? So that's where I found a lot of the gap was. The quantitative research, when there was limited to carbon emissions, greenhouse gas emissions. So I tried to extend this. Established environmental performance metrics aren't also well established there. So we sort of target. It's a very new, it's a beginning. I like to present what I call the triangle of environmentally responsible supply chains. Three main focus. One is, okay, how do I measure? So what are my environmental performance measures? Then there's the supply chain modeling, and then there's analyzing the system, and they all interrelate with each other. Now, each industry varies different. I know it's kind of small, but for the The first four squares is a selection of the industry. So the automotive industry or a general manufacturing industry will be very different from electronics industry, from a chemical industry, or from a pulp and paper. My research, I tend to focus on general manufacturing, which is a sort of a subdivision or a generalized version of the automotive industry, for example. The supply chain model, just a selection of how many items. So the first one I say is a single product or a single item. Then it's the number of tiers. I'm working on a 2-level tier project. Is it forward or closed? My current research will include both. And then at the bottom is the type of the coordination policy or scheme. So there's classical models, vendor managed inventory with consignment and so forth. And for the systems that are covered in gray, my methodology is basically, okay, we look at the system, we analyze it, how can we measure it, then we model, and then we optimize. So basically, okay, what is the supply chain? We talk. So it's simple animation to explain it. Christmas is close, everyone wants Christmas trees. So the customer, he wants to buy a Christmas tree, he goes to his Walmart to get or wherever he goes. And then the retailer says quick to the manufacturer, prepare a Christmas tree and send it over. Manufacturer goes to the supplier, quick, I need some actual trees and so forth. So this is what we like to call the information flow. It's going from the customer backwards throughout the chain. And the forward flow would be the material. So the supplier quickly would manufacture whatever product he wants, whether it's the Christmas tree or the gifts that someone wants to buy. Puts them on trucks send them to the manufacturer starts producing, adds value to these products, puts them on the trucks again, send them to the retailer, and in the end, our customer is happy, he can buy whatever product he wants. So this whole process of the information going forward and the transfer of the products from the supplier through the manufacturer, through the retailers to the customers, what we call the supply chain. A 2-tier supply chain is a very simplified version, is where I could take a vendor or a supplier, in my case it would be a manufacturer, and the buyer or a retailer. And there would be the transfer of the products from one side to the other. Now there's different coordination schemes that could be used, such as vendor managed inventory, consignment stock, the classical one that's proposed by Hill and so forth. In general, the concept is, what is my supply chain cost? So they say at the retailer he has holding cost. And there's holding cost at the manufacturer as well. Setup cost for producing these products and a ordering cost at the retailer. These are my 4 main cornerstone financial costs that people consider. So I call these the supply chain cost. And I said, okay, let's introduce greenhouse gas emissions and energy. Because when we focus on saving the environment, we realize that these are very 2 important things that we want to present. So it's a coordinated 2-level supply chain, in my case a single manufacturer, single retailer, and we're also talking about a single item. We consider greenhouse gas emissions from manufacturing, from transportation, and there's penalties according to the European Union. If you exceed certain limits of greenhouse gas emissions, you are penalized for it. And then there's the energy associated with these production. In my case, I considered the facility, I simplified the whole manufacturing facility into a bunch of machine tools, and that's what I modeled. So there's 2 coordination schemes we used. One was presented by Jabr et al. In 2003 for a classical coordination. Basically, you are producing and then you ship. You produce and ship, you produce and ship. And the second one is a vendor managed inventory with consignment stock, where you are producing and shipping and you are storing at your buyer. So what we did was basically we had our supply chain costs, the 4 main cornerstones. We had our costs from greenhouse gas emission from manufacturing, greenhouse gas emissions from transportation, penalty costs, and the specific energy consumption. The objective was to minimize these total costs. We were optimizing the production rate of the facility and the number of shipments between the 2, the buyer and the retailer. So we had a nonlinear mixed integer programming problem. I used Excel with a problem solver and enhanced it with some Visual Basic macros. So this is just the maths of the 2 equations. I did extensive sensitivity analysis. I'd just like to present here. The orange one is the classical coordination, and the second one is at the vendor managed inventory. If you notice in both cases, for the production rate, there's a part where it's really flat, and it's basically, that gives us as a manufacturer a little bit of flexibility, where I can vary my production rate up and down, and still there won't be that much of effect on cost. in general. The little ups that you see are basically the penalty costs. When you exceeded certain greenhouse gas emissions, a penalty was applied, and so you see that type. So if you have a facility that's operating under high production rates, you would probably want to operate using vendor-managed inventory, for example, as opposed to a classical coordination. Now, the other thing I wanted to bring attention to is the recovery operations for products and material. And there's a general hierarchy. The first thing you want to do is minimize resource use. And that's why I focused on energy at the beginning. You want to maximize the life of your product. You maybe apply minor repairs, remanufacturing, refurbishing, recycling, disposal. So you want to stick with those first. And the last thing you want to do is dispose of your product. So in the second part of this, of my study, I decided to add the closed loop, the reverse part. So we have production, serviceable stock, and then you sell it to the market. And then from the market, I collect it back and I remanufacture. So this is not a two-level supply chain. In this case, it's just a one level. I'm focused just on the manufacturer, but I'm introducing the reverse. And so it's a single-tier inventory problem. There's a finite number of remanufacturing is possible because a lot of the studies suggested that, oh, you can just keep remanufacturing. But the case is no. I can only remanufacture a certain number of times until the material that I'm using or the product I have loses its characteristics, loses its quality, and I can no longer reuse it or remanufacture it. And the environmental considerations, again, were the energy, greenhouse gas emissions, and the solid waste disposal. So those are the list of my system costs that we used. And now this problem, I try to apply a non-classical approach because it's very hard to add financial costs and environmental impact. In my first study, I converted everything into cost, but that basically what it does is you're just trying to avoid being penalized as opposed to protecting the environment. So what I'm suggesting now is that we have a non-classical approach where basically I find a reference and now I can add my apples and oranges. So I have my system total cost is what I refer to the financial costs. Then there's the greenhouse gas emissions, there's the energy that I consume, and the solid waste that is out from my system. Now, in general, the economic order quantity is one that I use when I optimize my supply chain for cost parameters only. So I use that as a reference. I took that optimal policy and I applied it and I obtained a reference cost, a reference greenhouse gas emissions level, reference energy, and reference waste level. And then I applied my new model and I was able to get costs and I sort of divided so I get them as fractions. I'm trying to minimize this. So I have 4 decision variables, which is my lot size, the number of remanufacturing setups that I'm going to have, the number of production setups that I will have, and at the end is the number of times that I can remanufacture. And there's an investment cost associated with that as well. So if I want to be able to remanufacture a product 7 or 8 times, there's a certain investment that goes at the beginning of my setup to ensure that I can design a product which can be remanufactured numerous times. Yep. So modeling that, being multi-objective with multiple decision, was very complicated. What I have done for now is just simulated certain things to understand certain relationships before I get into the final model. And I realized that if my focus, the managerial focus, was on minimizing costs, my greenhouse gas emissions, energy, and disposal wastes will all go up. However, if my focus was on to minimize greenhouse gas emissions, my costs increase, my disposal waste has no effect. However, my energy could increase or decrease. And that's because basically the relationship between the production rate and the greenhouse gas emissions is quadratic, whereas the energy is basically the more, it's not linear, it's exponential, but the higher your production rate, the lower the energy, the specific energy required for the machine tool is. So depending on where your current production rate was, if I was already operating at a high production rate and I'm lowering it down to minimize my greenhouse gas emissions, then my energy consumption is going to increase. But if my facility was operating at a lower production rate in general, and so in order to reduce my greenhouse gas emissions, I'm increasing my production rate, then my energy would decrease as well. And minimizing energy, you're costing greenhouse gas emission, and if you're trying to minimize disposal waste, everything else would increase. So as you can see, there's lots of trade-offs here. What is more important? So current stakeholders, for example, would include the government, municipalities. A lot of the focus is being given on, let's reduce greenhouse gas emissions. And when that happens, sometimes my energy consumption goes up. And we all know, it's not considered here, but when you acquire this energy, there's greenhouse gas emissions also associated with the acquisition of this energy, especially if it's not from green sources. So just focusing on greenhouse gas emissions alone is not. So this is just, if I started to extend the model a little bit, now if I see at this middle, I have one manufacturer who could have several suppliers, several retailers. And in the end, his customer will have a collection for the reverse process. There's collection and inspection processes, disassembly, repair, and recycling. So it gets complex as you go along. I've been using an input-output analysis currently. So this is just a small scheme of the current model I'm working on right now. So I have one manufacturer and one retailer. So I'm combining both parts now of the research. And between the manufacturer and the retailer, I can have the different coordination schemes. There's my suppliers up top for materials and components. There's my end customer, and we have collection and repair and recycling facilities. There's a T between each because there's fuel used for each of these trucks and the emissions associated with it. And with the input-output, we focus on certain things like, for example, at the manufacturer, we have greenhouse gas emissions, there's other emissions, there's waste, there's chemical wastes, there's water consumption, there's noise. So all of these still need to be included into the model. So just to conclude, there is a need to be environmentally responsible, and the mathematical modeling of our supply chains should reflect this. Current or immediate concerns would be focusing on energy, because if we look at that general hierarchy, you want to minimize resources that are used. So focus on energy, focus on greenhouse gas emissions, solid waste, and fuel consumed. And then eventually you might want to consider for the research being multiple products in the supply chain, or even if we're still focused on a single product but splitting it up, so the bill of materials, having assemblies and sub-assemblies, multiple tier supply chains, to customize it to different industries, so pulp and paper, electronics, the environmental performances, other things would be more important, customization, and then expand environmental considerations such as toxic chemicals, thermal pollution, noise, and so forth. And with that, I'd like to thank Dr. Jaber, Ryerson University, and NSERC for funding my research, and I'm open to any questions. Yeah.
You were saying something at the beginning of your presentation about a one-level analysis. You bring up terms so that I want to make sure I understand it in context, because, you know, I've done like one level, two level in design of experiments and this type of stuff. What does one level mean in the context of your supply chain stuff?
Okay, so I'll just go back to.
I want to make sure I understand that.
Yeah. So let's just assume this case over here. So I have a supplier, a manufacturer, a retailer. This would be considered a three-tier or a three-level supply chain.
Okay.
If I am considering the supplier and manufacturer, or I'm considering a manufacturer and a retailer, this would be two-level. And a one-level, in my case, what I have done is my two-level was between the manufacturer and the retailer, and my one-level has been just the manufacturer. So the first model, I had a manufacturer, a retailer, and a single product that was moving in batches from the manufacturer to the retailer.
So your one level is going to be the dynamics of what happens within the manufacturer. So
yes, in the one level, what I've considered is the manufacturer producing items and selling them directly to the customer, and then collecting directly from the customer and repairing and remanufacturing.
Okay.
That was the one level.
Okay.
And then just to extend it to this, the mathematics becomes very, very complicated.
Are you considering at some point to see the impact of milk run waste? You know that model?
Sorry, no, I'm not familiar with.
Okay, in Mexico we used to use milk run waste. It's the name of the model.
Okay.
And it's quite interesting for this because.
Yeah, I'll make note of that one too.
Okay.
Is your simulation also done with the solver?
Yeah, what I've done was I just basically added some Visual Basic, some macros in Visual Basic to run the different. So for the first model, the production rate and the number of shipments. So I can variate the different production rates. There's numerous input parameters. I just have a quick. So I'll just jump. Jump down. As you can see, these are all the different input parameters that I have. So just to do sensitivity analysis, I have 4 decision variables with all these inputs. I would basically choose a specific scenario. So I would assume, okay, if I'm targeting, because I think practically a little bit from my consulting experience. So if I'm a company, what is my current situation? Okay, I have a product that can be remanufactured, for example, 3 times. These are my current setups. This is the current policy that I'm operating at. And then I would sort of vary it. Okay, what would happen if my setup costs increase? What would happen if my holding costs were to increase? What would happen if the penalty scheme for greenhouse gas emissions would increase or decrease, or energy? And I would sort of play around with these. So I'd variate those with the Visual Basic macros and rerun the model again. Yeah.
Any other question?
Yeah.
Right. First of all, I should admit that my knowledge about this supply chain management is really limited. But just to help me understand this, so you consider the investment cost for remanufacturing certain products. Well, would you need to consider the original investment to produce the products at the beginning, or it's just the investment part for remanufacturing? That's the first part of the question. The second part is your research is about minimizing cost. How would you relate that to the ROI, the return on investment? Is there a new relationship, or is it just different stuff there?
Okay, well, to answer the first thing is, in general, with the supply chain costs, so for example, you notice that I didn't include, for example, production costs. Because all that would do for me, because I'm trying to optimize my policy, which is optimizing the number of batches, the number of setups that I have, or the number of shipments between my manufacturer and the retailer. So if I introduce, for example, just production costs, all that's going to do is just raise the overall level. So my policy is going to be the same, but my total cost, instead of being 10,000, will be 25,000. It's still the same. So the investment cost that you're talking about associated with the actual design of the product and everything is just going to lift my whole curves and everything up. It doesn't have any effect, so we tend to ignore it. We focus on those that actually affect the decision parameters. When we started introducing the number of times a product could be remanufactured, it's with this equation. So there's an investment cost associated from El-Saadani et al. In 2013. They basically said the previous research that's been done with reverse logistics have considered that any product could be repaired or remanufactured an infinite number of times. And that really doesn't make sense, because every product, when you remanufacture, you're losing some of its characteristics or losing some of its performance. So after a certain time, you can no longer remanufacture or reuse it. So if you want to do so, he was saying, well, there's a certain investment associated with the design process, with selecting materials, which would increase the product. So I have to include it in my model, because now if I'm saying I want to remanufacture 5 times to reduce the amount of waste I'm going to have into the system, well, there's a cost associated with redesigning your product in order to be able to do so. Yeah.
And the second part of
Yeah.
the question, how is the cost minimization related to the ROI, the return on investment? Is it related, or is it just completely different?
It's not completely different. The idea with the return on investment, you're basically saying, okay, this is the amount of money I'm putting into this project, with the infrastructure, with my operational costs and my running costs, and when am I going to make this money back? What I'm doing here, though, is I'm calculating this system that I have of me selling products from point A from my supplier to get my product to the end customer. Basically, so I'll explain it. Here's a little story. My customer says, I'm producing this product. I'm just trying to find a simple way to explain it. So I want to sell you a product for $100. Me as a business, if I'm going to sell it to you for $100, I want to get it to you as cheap as possible. Maybe 40 to 60% of a product's price is just material handling and transportation, whether within the facility or to the customer. So the more effective or the more cheaper I can get it to you, either the more profit I can make, or maybe I can reduce that price from 100 to 80, for example. So basically, I'm calculating this supply chain cost. This includes the costs associated with getting my product from raw material all the way until it's a final product to the end customer. And the cheaper you can do that, the more beneficial it is for the business and overall. So if I'm just a manufacturer, I would calculate something called my economic production quantity. So here's a production rate that's economic for me as a manufacturer to produce the product cheaper. Now my buyer would calculate the economic ordering quantity, where he would have a different policy. He would say, let's say the manufacturer says, I'll ship you 100 items in one shot. Whereas the buyer now, my retailer, would do his calculations and he would say, no. You send me 2 shipments of 50. That's what's optimal for me. Now, if the buyer operated at his optimal scenario, that's not optimal for the manufacturer. If the manufacturer operates at his optimal, it's not for both. Now, when we combine both together under one centralized policy and I optimize, there's benefits, savings on both sides, which later on through contract they can decide, okay, do we split the benefits 50-50 or not? Now, the more complicated the system becomes, the more cost parameters there is or environmental concerns as we take into consideration. So that now our system is not just financially or economically beneficial, but also we take into account the environmental impact. So it's a little bit different from the return on investment.
Can I ask
Yeah.
one more question, please? Right, because you looked at the investment, the thing. So, in terms of the profits that they gain, actually, for the manufacturers. In average, how much do they gain in terms of these, profits? For example, for the laptops, right? My understanding is that retailers, they get them very cheap. You are talking about $25 or maybe $50, and they sell them with $500 and $600. Is that really the case, or is it something different? Does this apply to the automotive, industry? The concepts are the same. The exact numbers I'm not aware of. But for example, Dell, in general, Dell for the most part, has eliminated the retailer. You go to Best Buy and you want to buy a Dell laptop, he doesn't have any. You go online now and you order from Dell, and Dell would assemble the laptop to the configuration or the specs that you want and mail it straight to you. And even and now Amazon and all these online stores and onlines are trying to eliminate one of the steps in the supply chain to reduce their costs. But the actual costs of how much it costs here and there, I am not aware of. Even with the industry that you are involved in?
Well, if you look at the numbers that I have so far that I'm using for the simulation, I've adopted them from either the case studies or previous research. So general things, for example, sometimes you'd find that the holding cost at a manufacturer maybe would be, let's say, for example, $4 per item. Maybe could even be $400 per item. But
there are cases with that.
There are cases, of course. So, for example, to give you an example, if you're at Walmart, the holding cost of cereal boxes is a lot different than the holding cost of medicine at a pharmacy. Right? Maybe there's fridges associated with it, specific, temperatures, controls. A classic example of vendor-managed inventory would be if you have a fleet of helicopters, for example, let's say ambulance helicopters, and your spare parts for the helicopter need to be stored near you. These are expensive, but you basically, let's imagine you have a helicopter, all of a sudden it breaks down, and you are located here in California. Now the spare part is located where I'm from, in Toronto. So you need that component. You're going to phone me, I'm going to package the spare part, fly it to you, because you can't have your helicopter not running. It's an expensive piece of equipment that you want running, available all the time. So you say, okay, but I don't want to buy the spare part and keep it located at my facility because it costs too much. So I'll say, okay, let's have a vendor managed inventory system or a consignment stock policy where it'll still be my spare part under I'm paying the insurance, I'm paying these costs for it, but I'll store it at your location. So that's an example of something that can be very expensive, spare parts for the helicopter. So it varies differently from industry to industry and from product to product. But the concepts are the same.